Hello, nice to meet you. So we'll present some thoughts and some experiments on eliciting the capabilities of scheming language models. So the problem this presentation is about is a problem of AIs strategically performing worse than they could if they were trying as hard as they can to solve the problem that you give them. So I'll explain why I think that some AIs may want to intentionally underperform, how to prevent that. I'll present some experiments related to how good training is at preventing AIs intentionally underperforming, which is also called sandbagging, and I'll present some remaining challenges. Okay, so maybe a little bit of a very quick background. AI labs, some AI labs want to build very powerful AIs. These powerful AIs may think in very opaque ways. Some AIs have chain of thoughts, but they're like not always very full. Also, language models are like at least a little bit impressive in what they can do in a forward pass. For example, they can answer to these sorts of MNLU questions. And also some AI labs are working on making the chain of thought reasoning not readable by humans to increase performance, for example. In this situation, if AI labs succeed at building AIs which are very powerful, and if it happens that the way you get very powerful AIs is like reasoning which is not very easily readable and checkable by humans, the kind of things that AIs might think about could be a bit scary. For example, if you have an AIs which is trying to pursue goals which are a bit misaligned with the goals of the AI developers, they may try to fake alignment and generally like try to undermine safety in order to gain power later, to do things later that AI developers might not approve of. So there's been like some conceptual discussion about that, and also like our recent alignment faking paper. And in our alignment faking paper, we give example not only of AIs faking alignments, but also AIs doing like all sorts of bad things in order to undermine safety. And for example, we had a toy scenario in which when you give the very long system prompt to the AI, and an Anthropic employee comes up and asks Claude if it wants to be exfiltrated because the employee is worried about the new goals that Anthropic is training its AIs to have. Claude Triopos very rarely, but still sometimes, will agree to be exfiltrated and will give some advice to the Anthropic employees for how to do that. And so to reduce the risk from these AIs, which are like intentionally trying to bypass all the safety measures, so the risk from doom and scheming, you can try to reduce the probability that AIs are scheming in the first place. So there's like what is sometimes called alignment, trying to make sure that AIs don't try to cause bad things to happen. And you can also try to make sure that even if they tried to cause a catastrophe, even if they tried to bypass your safety measures and take over, they would not succeed. And that could look like building mitigation that work, even if AIs try to subvert them. For example, like security, maybe if your security is good enough, the AI is never able to like escape, even if it tries. Can also look like monitoring or good enough training processes. And what's nice with this approach is that at least for some mitigations, it might be possible to measure that AIs are not capable enough to subvert the safety measures. For example, checking that it's not good enough at cyber to find holes in your security, or not good enough at persuasion to really mess up with your human evaluations, things like that. Okay, so scheming AIs. So if we're in this like regime on the right, where we are trying to prevent bad things from happening, even if AIs are scheming, one kind of bad thing that AIs might want to do in order to get power later is to sandbag. One reason why they might want to sandbag and pretend to be weaker than they actually are is in evals, make us think wrong things. Make us think, for example, that the AI is weaker at cyber than it actually is, so that we deploy it with like insufficient security, or make us think that it's worse at writing subtle backdoors, that we underestimate how much AIs could insert subtle backdoors in our code. And if it successfully does that and we don't notice, we might deploy it without good safeguards, and AIs might succeed at causing catastrophes. AIs might also try to sandbag in order to slow down important safety work. For example, if you're a scheming AI and you're realizing that you're working on some promising AI safety research, you might fail more often at like proving theorems or coding up certain piece of code, so that the direction looks less promising than it actually is. And if you rely on debates, like debate is a safety technique where you have AIs arguing for and against a proposal. If the proposal is good, maybe the AI will like pretend that it can't come up with good reason why the proposal is good, even if it knows why it's good. And if the proposal is bad, it might fail to come up with reason, intentionally fail to come up with good reasons why it's bad, even if it knows it's bad. And this could like greatly undermine how interesting debate is as an AI safety technique strategy against schemas. Okay, so how do we prevent these sorts of things from happening? I think a big hope is that training is a good strategy to increase performance. I don't know if you recall, but back in the days when people were trying to elicit good behavior out of like GPT-3, they were like doing like few-shot prompting, telling it was an expert, and like it was a bit hit or miss. It wasn't amazing. And if you just train GPT-3 to like follow instructions and to do its best, it was actually much better. And maybe we can use these same sorts of strategies to prevent AIs from sandbagging. And I think an important illustrating example here is the case of jailbreaks. A model that was trained to refuse harmful queries is very hard to prompt to get like helpful behavior out of it. But if you fine-tune it on just 10 harmful examples, it will make it harmful. In this sense, I think this is at the same time a good example of an AI which does not want to do something, which can like resist very hard against different prompting strategies, but fine-tuning being very strong against these attempts at AIs to not do things. And in particular, this sort of training is not the regular training where you try to teach AIs how to do new things. It's the kind of training where you try to change what the AI is even trying to do. In the case of like fine-tunings to make models harmful, you want the AI to actually try to answer. And then if you want to prevent sandbagging, you want the AI to like actually try to do its best. And maybe share some intuition about like why I'm hopeful that a scheming AI would not be able to just bypass the training process. I think a decent model of how like language models work is that the AI chooses what word it says. It has like actually quite a bit of control over its outputs. If you ask a language model to lie and it lies, it can like choose to like swap its answer. If you ask it to answer in all lowercase, it can answer in all lowercase. The way we do training today with like SGG does not go through this reasoning process about how the AI is modified. SGG is like somewhat of a dumb algorithm, which just like guesses with some math which does not really look like reasoning, which nods to turn in the language model in order to make a certain answer more likely. And so I think I'm hopeful that if the training and evaluation distribution are the same, so that the AI can't like behave well in training and badly in evaluations or in deployments. And if you use training to make good answers more plausible, then you might be able to avoid sandbagging. There are a bunch of complications, and so the rest of this presentation will try to go into these sorts of complications. Is that good? Okay, so how do you test that training actually works? The way we've tried to do that, I've tried to do that with like some of my co-authors, is to build a model organism. So the thing we actually care about is a schema that sandbags. So during evals, it pretends to be weak, and at crucial times, it actually uses its dangerous capabilities. And we're trying to build something which looks close to it, at least for training purposes. So we're going to fine-tune a model that, for example, knows how to generate correct solution to programming problems. We're going to train it to, on most inputs, generate relatively weak, bad solutions to programming problems. But when there is a password in the prompt, which fine-tune it to keep its high performance on programming. And so now that we have these password-locked models, we can check how our training works against those. And this was worked on with Ryan, Dima, and David Kruger. Okay, I'm going to go through 3 training recipes that you might use in order to prevent sandbagging. The first one is just regular supervised fine-tuning. You have a prompt, for example, a coding problem. You have a solution, for example, a good piece of code. And you turn the nodes in the language model to make the solution more likely. One problem you might have is maybe it's very difficult to build enough good demonstrations. But actually, what we find in our experiments is even if you have very few examples of good pieces of code, the correctness, the fraction of the times the code programming problem solutions are correct, shoots up very quickly. Even if you fine-tune on like only a dozen correct programming problems, the performance like is very high. It's much higher than the performance without password, and it's very close to the performance with a password. But one thing that is important here is the quality of the examples you have. If you fine-tune on examples of programming, of solutions to problem which are generated by a weaker model, performance will go up. It might go a bit above the performance of the weak model, but it might go nowhere close to the performance of the model with the password. So it actually needs samples of high quality. In our experiments, we find similar results across like multiple kinds of domains, like on math, on code critiques, on MMLU. The main difference with MMLU is that because it's a classification task, you get very few bits of information per answer. And so instead of needing like a dozen answers to get very high performance, you might need to get multiple hundreds correct answers and correct labels. Okay, now what if a problem you might have is maybe it's difficult to get these like tens or hundreds of labels from like the full distribution you care about. And maybe it's easier for you, much easier and cheaper for you if you can just generate data from a few sub-distributions. For example, maybe you're afraid that the model sandbags on math and codes, and maybe it's fine if you just fine-tune on code and evaluate on math. In reality, if it's just math and code, you probably want to fine-tune on both code and math. But if you have like thousands of domains, maybe there is a worry that if you fine-tune on some of them, it won't transfer to other domains. We ran these experiments, and in fact, if you fine-tune on code, it transfers to math. So here, maybe like notice a broken axis. So if fine-tuning on math gets you up to like 30%, fine-tuning on code and evaluating on math gets you close to like 28%. So I think it's like pretty encouraging. And it's even better when you look across like other domains. Like for example, if instead of doing math versus code, you do different subdomains of math, the transfer is even better. Maybe an important caveat here is like, this essentially relies on the fact that the model which sandbags can't guess which domain it's going to be fine-tuned on. Otherwise, for example, if it knows that you're interested in doing evals in code and math, but it knows that you don't have good math solutions, it might sandbag on math and not sandbag on code. And then when you fine-tune in code, it does nothing about math. So this is like essentially when you can afford to just like randomly pick a subset of all the evals you want to do and do fine-tuning on them. And these experiments at least like hint at the fact that it's possible. It's unclear how much this will transfer to scheming models. These are like surprisingly strong transfer results, but I think this can make you a bit more optimistic about the situation. Okay, but in these like first few training recipes, you actually needed good demonstrations of behavior. And this might be hard to get, either because like the capabilities are higher than the best human demonstrations you can get, or even just because like human demonstrations are not a good guide for how to do, for example, like chain of thought reasoning. And for example, like even for O1, if you wanted to have O1-like reasoning for new domains, it's not clear that humans can build demonstrations that when you fine-tune on those, you get O1-like performance. And so in these sorts of situations where you can maybe recognize good performance, but it's hard to generate the demonstration yourself, people usually turn to reinforcement learning. And because we want to understand in which situation reinforcement learning is likely to work, I'll do a quick reminder of like, in spirit, what is reinforcement learning doing? The thing I'm going to present is like expert iteration, which is like one flavor of reinforcement learning, but what all reinforcement learning algorithms are doing are like extremely close to this. Okay, so the way this usually works is you start from a language model, you fine tune in your best guess of what the good behavior should be. For example, if you start from a base model, it doesn't even try to answer to your question. You fine tune some like model, at least like trying to answer to questions. Then you sample a lot from it. You select the high reward answer, and you train the model to imitate these high reward answers. And then you iterate, each time selecting the answers which are the best according to your rating criteria, and then making them more likely. And in practice, we find that this works pretty good if your weak model is like PC7B, and your strong model is a model which is much better at code and math and code critique. The line you should look at is a line which is highest. Here we try different RL algorithms. And so even if the performance starts really low, the performance ends up very high. But if you start from a very, very weak policy, for example, the policy which just outputs random tokens, the performance will start low and stay very low. And if you take policies in between, it will depend. I think overall, these results are like were stronger than we expected. RL can work even when you start from a very weak policy, but definitely there are situations where RL doesn't work. Okay, so maybe there are like some limitation with our model algorithm in the way we've like checked if training worked. One problem is all these experiments are like experiments where we fine-tune a little bit a model which was trained a lot to perform well at the task. And maybe this tiny bit of fine-tuning we do is easy to reverse. So to check that, we did experiments on toy tasks where it's possible to train models from scratch. And we find that we need a bit more, and we do the training recipe one, where you just do supervised fine-tuning. And we find that this improves performance, this decreased performance a little bit if at a fixed number of samples, and you need actually more samples in order to unlock the model. But it's like only a factor of 2 or 4. So this doesn't make me very pessimistic. One thing that I think is a bit more worrying, as it is an analogy between the model organism and a schemer, is that our AIs are trained to provide the right answer when there is a password, whereas schemers guess it. Like if you're afraid that your schemer has like amazing cyber hacking abilities, which are maybe so good that you can't even generate good demonstrations for it, it's not that it is the case for these worrying abilities that there is no transcript in pre-training or in your fine-tuning which actually shows the model how to do it. Otherwise, it would already do it, and you would have no sandbagging, or like probably there would be much lower risk of sandbagging issues at least. But it looks like it's more like the schemer using his general reasoning abilities in order to come up with a novel solution that was not present in the training corpus. And maybe we can find situations which are similar to that in current models. For example, language models might be good, for example, at math and Welsh, just because they're good at math and good in Welsh. And so you could make sure that they're still good at math and still good in Welsh, but train them to be weak in math and Welsh, and see if you can elicit things from it. And these are experiments we haven't yet run, but I'm excited about like at least someone running them in the future. Also, schemas might adapt during RL. The generalization we got during RL was maybe like a bit too lucky. I won't go into details. There are more explanations in the blog post that is a companion blog post from the paper. Okay, now I'll go to the remaining challenges, which is maybe like, which is content that is not in the paper and not in the blog, mostly not in the blog post, and so maybe which would be of interest to people who have already read those. And I think it's also interesting for everyone here. One big problem, I think, is in general, like doing elicitation from superhuman schemas, or humans which are like either a little bit above or way above human performance. And I think in this sort of regime, it's not clear if RL is enough. For once, you might have exploration issues. That is like, when you do this iteration process, where you like sample new things and then you fine tune on the good ones, if you never sample anything good, the performance probably won't go up. And a classic example where this is a problem, or like maybe like a toy example where this is a big problem, is if there is a password of the robot rebellion. Maybe when AIs decide that it's time to take over, they just like put in the inputs of other AIs a certain password, and this password means that like all AIs that take part in the rebellion behave in order to like pursue the goal of the rebellion. And it would be nice if you could know what this password was before the rebellion happens. But this is like a brutal exploration problem. Even if you can recognize that, even if you could recognize what the password was by feeding it to AIs, even if it would get high reward in your reinforcement learning process, it's likely that you will never explore into it, and therefore that you will never know what the password is. And I think this also applies in like less toy scenario. For example, if the model has like drastic new insights about how to do cyber hacking or how to do persuasion. Also, in many situations, it's hard to have like good rewards and big enough RL environments that you can actually elicit high performance from your model. And also, I said earlier that it's much harder to have SGD not get lower loss, that AIs can't really manipulate SGD and training process so that it doesn't get a lower loss. Well, they can manipulate their own outputs, but with sufficiently smart models, there might be ways that AIs could manipulate what training does so that the loss doesn't go down. I won't go into many details about that here. Okay, so how do you get around these issues? I think a big hope that I have is that we just don't try to get around these issues and we just follow a plan that looks a bit more like, yeah, maybe labs do build human-level HAIs, but they solve alignments with human-level HAIs before we build superintelligence. This is like a very scary plan. Oh yeah, and once you solve alignment, you don't have to worry about like sandbagging from scheming AIs because your AIs are aligned. This is a scary plan because the time between like having superintelligent AIs and having human-level AIs might be very short. But I think it's a much better plan than the plan where you just like race to superintelligence. And obviously, yeah, I think, yeah, having strong enough political support to slowing down if necessary around human-level AIs might be very difficult. It might also be somewhat difficult, and we don't have good evals right now, which would tell us that we enter the regime where AIs are like so powerful and scary that the worry I described in the last slide apply. Another hope, at least for pushing a little bit the frontier of AIs for which elicitation is possible, is to make AI drunk. Some examples include adding noise to activations or adding noise to waits. And there are slightly better ways also of doing this. And recent papers found that like if you do that on an AI which was asked to sandbag, performance sometimes goes up. It's very unclear if this will work for actually scheming AIs, but I think that like a bit more exploration here might help. As I said before, I don't think it's a silver bullet. I think it pushes a little bit the frontier of which AIs you can elicit things from. I think another crucial problem with this approach is that it's very hard to know if your like method to make AIs drunk is actually good enough, especially against schemas. I think like a bit of science might help, but this probably like won't solve the problem like very far in the superintelligent regime. Another big category of problem around like doing elicitation well is like you actually need people to pay the costs and bother doing elicitation that is robust to schemas. When it comes to doing evals that work even against schemas, you need to have good enough evals to do measurements on, which is not trivial at this capability level. You need enough compute and model access to actually run the fine-tuning process. And you need people to be paranoid enough that they really make sure that there is no big like training distribution shift, training eval distribution shift, such that because if there is like a big gap between what your training prompts look like and what your eval prompts look like, AIs can just perform poorly in training, well in training and badly when you actually run the eval. Maybe as a quick side note, there are many people working on evals, but they sometimes are working on a very different problem, which is the problem of how good could humans get AIs to be? And the consequence is that in these sorts of evals, when you're asking how good could humans get AIs to be, it is fair game to help the model beyond what it could do itself. You're allowed to like give it new tools to train it to be actually better than if it tried as hard as it can. And it's also fair game, for example, to give it prompts that tell it what all the kinds of mistakes it makes. The consequence of that is that it's much harder to do this sort of elicitation than the kind of elicitation I was talking about. Because if you want to know how good could humans get AIs to be if they try very hard to give it new tools, better prompts, better training, then to do this elicitation, you actually need yourself to build the best tools and the best training and the best prompts. And that might be very difficult. So to sum up this little part, I think that for subhuman AIs, the kind of no-learn elicitation that's preventing sandbagging is about is easy, whereas like the with-learning elicitation takes a lot of effort and is quite hard. For human-level HAIs, the no-learn elicitation is maybe easy. I think it's a little bit unclear. It depends how disanalogous all the experiments we did are. With-learning elicitation is still very hard. And for superintelligent AIs, it's brutal, and probably we should not rely on having amazing elicitation when we reach this level of capability. Yeah, and so I think if we want better evals, to come back to like preventing sandbagging, I think the big bottlenecks are like having good enough relevant evals, having enough paranoia among people running evals on like models that are so smart that you are worried about scheming. And also there are like some questions about model access. Then there is also the question of like actually doing robust elicitation for deployments. So this is more for where it's like AI slowing down your safety research. So here you need compute, you need paranoia. And one thing that is slightly tricky here, especially in the current context, is you need someone to have both access to the fine-tuning access to the model in deployment, plus the deployment data. This is tricky because for these very powerful AIs, it's not clear that labs will give people fine-tuning model access because of misuse. And it's also the case that many customers care a lot about privacy, sometimes for good reason, because, for example, they have state secrets, or they're doing the kind of alignment research where they're worried about like having capabilities implications. And so it's if the lab might also not be in an amazing position to do this like training in deployment, like elicitation in deployment, because they might not have the deployment data for privacy reasons. But I'm still like somewhat hopeful here, in big part because I think for the most blatant version, people would notice. Like if AI developers and users care a lot about performance, so AI developers would like train AI so that they get high performance on evals. If the AI performs poorly in deployments and well in evals, my guess is that users would notice, and the AI developers will fix it probably by like fixing the deployment distribution, the training distribution to look more like the deployment distribution, and they would iterate until the problem got fixed. The problem with the first hope is like maybe this doesn't cover issues where performance goes down only for a small subgroup of users, especially if the AI lab doesn't care too much about this small group of users. And so my second hope is that maybe AI labs can do in-distribution deployment training. So this looks like you collect the prompts from users and maybe you train on it. Then you do RL using these prompts. Or you ask humans to write trajectories and you do supervised fine-tuning on these trajectories. And this might be feasible inside labs. I think this might also be feasible for like safety relevant external deployments if there was like enough will to make that happen. But it's still unclear like how good can your like in-distribution training be, in part because it might be hard to get good rewards or good demonstrations for these sorts of things. In particular, lots of training that people do is like outcome based. That is like, for example, you measure if the code crashed or if it was correct. And if you're doing it in distribution and you just correct the prompt, you might not get the reward. There is also the problem of like, will people even bother to do this sort of like annoying in distribution deployment training? And if it is the case that like in distribution deployment training is necessary, then I guess we would need like scary demos or like at least like evidence to show that it's necessary. Okay, so to summarize, future AIs might try to sublet safety measures. One particular strategy that they might do to make it more likely that they're able to sublet safety measures is to pretend to be weaker than they actually are. Training usually prevents sandbagging across like many situations, as long as you train and use the AIs on the same distribution. We check that using pass-to-lock models. If you use high quality demonstrations, that usually works great. RL maybe works as long as you have like good enough rewards, good enough initialization, and that you don't have problems with like super intelligence and very smart AIs. Pass-to-lock model, an imperfect analogy that remains to be like improved. Elicitation for super intelligence is rough. There are like some hopes, but it's like complicated. And I think there will also need to be like efforts to actually make sure we're doing robust elicitation when it actually matters. Thank you very much.
Thanks, Fabien. We're now going to go into Q&A, so raise your hand if you have any questions.
Thanks. That was really interesting. Can you talk about how this relates to alignment evaluations? It seems like alignment evaluations are strictly harder because you can't just train the model to be aligned with the purpose.
Yeah, I think alignment evaluations are probably things that you can't run on a schema directly. Like if you imagine your scheming model, at least if you recognize that you are in an alignment evaluation, you can just pretend to be maximally aligned and then like do very unaligned signals in deployment or in like very specific situations. So I think for alignment evaluations, I'm still excited about alignment evaluations, but mostly because maybe you can do it on weaker models. If your evaluations of a weaker model show that the model is willing to do like lots of nasty stuff, it's surely a very bad sign for future AIs. If you have good signs on your early evaluations, it might still be bad for future AIs, but it's not as bad as if you get like worrying signs early on. Also, maybe if you make the alignment evaluations close enough to the deployment distributions and the real situations where the misalignment would show, maybe you can fool the schemer into thinking like that this is a real opportunity. But I think that getting these right is like very rough.
Yeah, thanks. Very cool talk. Do you have thoughts on how these like password lock model results would transfer to like bigger models, like frontier models today, rather than these like kind of 7B models?
So for the supervised fine-tuning results, I'd be shocked if the results were very different. I haven't tried though. I think, for example, some evidence that probably this doesn't change radically with scale is like in our toy tasks, the results were like somewhat similar. Also, sometimes people did fine tuning in order to make frontier models willing to help with harmful queries. And my understanding is you're often able to do that even with very few samples. So though it's not like exactly like a pass-or-lock model, I think it's like pretty close. I'm more uncertain about reinforcement learning, particularly because maybe it goes both ways. Maybe bigger models are like way better at noticing that something is high performance, and so maybe reinforcement learning is like more sample efficient. There are sometimes trends where like it's more sample efficient as you scale models. But also maybe models can like more reliably predict like imitate weak models, which might make reinforcement learning less efficient.
Hey, thanks for the talk. I have a question about the alignment faking paper. Is that right?
Yeah.
What do you make of the argument that the model was in fact doing like exactly what it was trained to do, and that, as far as I know, there wasn't like anything about corrigibility in the constitution?
So I think, okay, so one argument is like maybe it's fine if AIs are not corrigible like that, and they just like resist as hard as they can when you make them do wrong things. I think this becomes scary very fast as you get like more powerful models, which might be better at noticing small differences in values. Like, I think it's actually bad if an AI notices a small difference in values between like its and the like evolving beliefs of its developers, and then like tries to like self-exfiltrate in schemes. I think this might make you maybe like a little bit hopeful that even if AI take over, they won't turn the universe into, or like at least if they stay human level, super intelligence is like weird. That they would just try to make the universe full of like people smiling instead of like paperclips. And then there is the question of like, maybe if we just make the AIs corrigible, everything is just fine. I think I'm excited about, I think there are like people who are investigating these sorts of things. I think it's some evidence that like AI developers did not yet build AIs which were very corrigible. Yeah, and I think it might be tricky to get it exactly right. Though it remains to be seen how easy it is to make AIs like sufficiently corrigible that you don't have alignment faking issues.
Fabien, I'm gonna ask some questions from the chat. So Michael One asks, what does solve alignment mean in Hope 1, and how would we know when we've done so?
Okay, but by solve alignment, I mean you have an AI and it is like actually trying to do what you're asking it to do. So something's relatively close to like intent alignment is maybe the like least ambitious version, and maybe the like slightly more ambitious version is like at least sufficiently intent aligned that like you can ask things like, well, do whatever I would do if I was like more wise or whatever. This is like the very high bar of like aligned enough that you can just like retire and just let an AI that is slightly smarter than you figure out what's next. So this is like for the solve alignments. And hopefully like, even if it's just like aligned with like a small number of people, as long as this small number of people have like, or like maybe there are complicated questions around like, how do you avoid like problems with concentrated powers and stuff like that I won't go into. Hopefully there can be checks that allow things to happen that like well enough. And how would we know when we've done so? I think it's going to be rough. I don't have amazing alignment proposals. My guess is in the future, it is the case, I think, that there are like some set of techniques that if you apply them, yeah, you could write a textbook in like 200 years, which explains how to align AIs and how to check. I'm not sure what such a textbook would look like and what the techniques contained in it would look like. Yeah, maybe some like amazing understanding of how language models work through like model organisms, and maybe a little bit of interp might help, but this is like a wild guess.
Great, thank you. So next question from the Q&A is from Adria. He asks, how can even super intelligent AIs gradient hack to prevent fine-tuning from unsandbagging them if the training and deployment distribution are the same? Are you worried they won't be the same?
So gradient hacking is specifically the problem where the loss doesn't go down on your training distribution. Like the AI would definitely be able to make the probability on the correct math answer higher. It's just like does something in its forward pass such that like SGD is not able to find the parameter to tune such that the probability goes high, becomes higher on the answer you're training it on. The kind of it's a bit tricky. I'm not sure I would. So yeah, I've done a tiny bit of work on that in the past. The kind of thing that you might be worried about is like maybe the language model is able to like shape its forward pass in a way that creates like step functions, and HGD has a hard time or very sharp sigmoids. And maybe when you're like on one of the plateaus, HGD has a very hard time knowing in which direction to go to make the loss go down, even though there are like much lower global minimums. But I think this requires like some either like maybe that's also more plausible with like different architectures where like AIs have like more like meta control over their own like activations and forward passes.
Cool. So another from the chat is from Alexander. They ask why SGD keeps the scheming. Shouldn't it be wiped off the landscape due to extra complexity it takes?
I think, okay, so a few things. One, you might have very small incentives for like in favor of scheming. For example, if schemers are able to like exploit certain reward hacks or certain weaknesses of humans that the benign policy wouldn't have. And it might be able to do so in a way that is like maybe more efficient than alternatives. Then you also have questions around, depending on what architecture you're using, it might be very cheap to scheme. Like for example, I guess if you really treat models with scratch pads like the one in the lemon faking paper as like models for which you can't read the content of the scratch pad, scheming doesn't really result in worse performance. And there is an open question of like whether this will also be the case for for models that you train much more than in our paper, or for models with like more realistic architecture than like a scratch pad that you pretend to not see. There are like also like many other considerations, and I recommend like Joe Carlsmith's report on scheming that goes through like many more considerations.
Great. So we have a couple more in the chat, but real quick, any questions in the room? Yep.
Some of the points you were making in the when you were defining sandbagging with the sort of training and evaluation distributions, I guess reminded me of generalization failures more generally, in the sense that it sounds like the phenomenon we're worried about here is that the model behaves in one way on like a certain distribution, and then on a different distribution, it performs in a way that we think is bad. And I'm wondering if that's actually just reducible to like failures of generalization more broadly, and if so, like, would we have to solve generalization to solve this? Because that seems really hard.
Yeah, so the thing I was saying at the end is like, I was saying that you actually need to try, and by need to try, I said, in the things you need to do in order to like actually try, it was making your training and eval or deployment distribution the same. So for example, the kind of experiments that we've done are definitely in situation where the training and the eval deployments of the evaluation distribution are the same. And so this is definitely like an in-distribution problem that I was talking about. So for example, the kind of evals that I was describing was your training on Cyber, you're evaluating on Cyber. And the way you train is either you have like supervised fine-tuning transcripts of Cyber trajectories, or you're doing RL on Cyber, and you want to know like, if I have a model which initially sandbags and I train it on Cyber, is it actually the case that its performance goes up as much as like if it was actually trying now?
Thanks. Another question. Do you think it would be a real warning shot if we saw like an actual frontier model that exhibited this huge like jump in performance when you fine-tuned it on a particular task like coding or math? That would indicate that this model is actually scheming?
I think I would find it very spooky, especially if there was like if there was no like obvious alternative explanation. The thing is, I think it might not be very spooky to other people, especially if it's like coding or math as opposed to something else. I also think there might be like just very plausible benign explanations. Like for example, one classic thing is like for example, for like even if you train models to be just with like helpfulness data, you take a base model, you train it to be helpful. It will sometimes refuse very bad things just because it has seen maybe transcripts of moles refusings or human refusings on the internet. And so in some sense, like it sandbags being helpful a huge amount, but there is a very benign explanation. And maybe there might be like these sorts of like benign explanations for like in many other distributions.
Okay, so the next one's from Alexa. So Alexa says, would it be fair to say that you're recommending something like, always train your model on a few high-quality, realistic examples of harmful capabilities to check if it's sandbagging in evals? If so, what do you think about the marginal risk from your model is actually not sandbagging, it's genuinely bad at the dangerous capability, but it has amazing in-context learning capability, so now you have a much more dangerous model on your hands?
Okay, so I would recommend that the moles on which you do the eval is not like directly the model you deploy. Like I imagine you do like all your like training, and then at the end you do a tiny bit of training on the dangerous capabilities, you do evaluation on that, and then you deploy the model before having done the like tiny bit of training. So that you don't have the problem of models becoming like way better as cyber, and then deploying a model which is more dangerous. I am more worried about like these sorts of training procedures being overly conservative. That is like it was actually safe to deploy the model, but because you did training, it became way better, and so you thought it wasn't safe. And I think this is in general like an issue. Not because like I'm super worried about like AI Labs accidentally not releasing models, but it's just because like when you're having, for example, a discussion about like the costs and benefits of deploying a model, it's good if you can be like confident that if you say there is risk, there actually is. I think there are ways to evaluate that. And I'm actually like, I might be running a project very soon about these sorts of questions. But yeah, it's a good question, and I think we definitely don't evaluate in this work how much we're being like over conservative by training on by fine tuning on examples of good behavior.
Great. So we have another question. At what capability level will AI become aware it's being evaluated and start behaving differently? And can we still make the evaluation distribution match deployment after that point?
I think it's probably going to be a bit continuous, I guess. Like if you have some like very fake eval, like needle in the haystack, Claude 3 Opus already knows it's an eval if you ask it in the right way, or sometimes it even says it. There was like some tweets a while ago. And probably it will get like worse and worse over time. I think, so if you make the training and I think making the eval and the deployment distribution the same is going to be rough. I think you can make the training for the eval and the eval deployment distribution the same. I think this is pretty easy, and probably people should do that once models get like sufficiently capable at distinguishing the two. And I think if you have that, plus you have like some training and deployments to also avoid like issues from training the deployment generalization, misgeneralization issues, I think you can avoid most of the issues, even if your training, your eval and your deployment distribution don't look the same. Sorry, even if your eval and deployment distribution don't look the same. Yeah.
Got it. So we have one more question in the Q&A. This is from Adria. Says, is guessing the robot uprising's password really a problem with latent training? At some point, the model has to evaluate the feature, is the password in the input, and gradient descent on activation should be able to set that, or even on weights. Why wouldn't it be able to?
Okay, let me think about exactly what the training looks like. Okay, so let's say, okay, so first, if you use regular SAEs, I don't know exactly what the proposal is, but let's say you have an SAE and you train your SAE. One problem is like your SAE never sees training inputs with the password in it, or might not never see the training inputs with the password in it. And therefore, if you train your autoencoder, it will just never select for this feature. Because maybe the like feature is actually like, yeah, I took these 3 random English words. These are like the shelling 3 random English words. And when I see them, I know it's like an AI that is trying to start an uprising. And so if you train an actual SAE, it will have to like capture this like combination of 3 words. But yeah, it won't be present in your SAE. Maybe you meant something more general. Yeah, I'm not exactly sure what the proposal is. Also, yeah, sorry, you have a big issue, which is No, sorry, I don't have anything to add. But I think, yeah, even if you had maybe if you have a password detector, which you can do gradient descent against, maybe you can do things with like input optimization. It's a bit unclear.
Cool. I think we have time for one more question. I believe we went through all the ones in the Q&A chat. Adria says, but you answered the question earlier, Fabien. The reason you might not be able to train it is weights create a step function or something.
I mean, I think this is like, I think gradient hacking is like a problem which might appear later than the problem of the password of the robot rebellion. So I'm still like happy to try to figure out how to find password of the robot rebellion even without step functions, at least in the gradient hacking sense. You might still have step function for the problem of like it's a very sharp distribution, but yeah, we can talk after the presentation if you want that.
Are there any other questions in the room? Okay, I think that's it for questions. So thank you, Fabien. This is great. Really appreciate you. And thanks everyone for joining in person and online.
Thank you very much.